Okay, recording started.
Right. Enjoy. Right. Welcome back to Lee Algebra. Today I'll be talking about charts, atlases, and manifolds. Very briefly, a summary last talk and last talk is we just got really good at doing calculus and differentiating on Rn and Rm. On that, I want to add a quick definition, which we might be using in the future. So let U be a subset of Rm and V of Rn. A map F from U to V is geomorphism inverse exists. So a map is a geomorphism if you can infinitely differentiate it. It has an inverse, and the inverse is also infinitely differentiable. This will appear like in two definitions in the future. Adding on to this, we have a really good understanding of how to take derivatives and do calculus on Rn. So the motivating question behind this talk is, well, can we do a little more than that? Can we do calculus on stuff that's maybe not exactly Rn? And so this leads us to our first sort of main idea, charts. I'll just write a definition and then we can talk about it later. Shoot. Right. So I will say that the names given to all of these terms are very self-explanatory. I will also draw an accompanying picture, which is if we have some set. Can everybody see? No.
Immediate comment. You spend a bunch of time writing something down, and then you didn't say at all what you were writing down, and didn't at all describe it. And you're already kind of moving on. No one has had a chance to read what that says.
Okay.
You should. No, don't let people read. Like, explain what you're
Right. We have some set like M, just like draw some generic set M. Then the coordinate chart is a sort of like, it's essentially, we're mapping some part of this set M onto a structure, say Rn, or Rm, most notably. So if we have, this is M, and we have some set U, this is our subset U, you have an accompanying map phi that takes this onto Rm. That's all the chart is. And I don't know, maybe it has some pretty nice shape, so we'll just draw it as a box, and this can be phi of U. This thing. That's all the chart is. It maps some set M or some subset of M onto Rm. given the name, it's a chart. It maps stuff. Charts have these two properties, which is that this phi of u is open. So in the sense we can draw some shape in Rm. We can it's an open ball. And number two is phi of u. Phi is a bijective map from here to here. I.e., if I pick some point, it's uniquely mapped to some unique point here, and I can always go back and forth between these two spaces. For extra notation, if this point, we call this P. If we have this point P inside of U, then the coordinates after the map, the coordinates of P all good.
Is there a glare on the board for other people, or just
Tiny bit on the Zoom, but it should be okay. So, as per the name coordinate chart, if you have some point P inside of your set M, then we've assigned it to some n-dimensional tuple, I guess. And these are like the coordinates. These are the coordinates of P.
why are we defining?
Are we not going to use this later?
No, but we're going to use this later. It's not a good enough reason to define something. Why are we doing all this? So go back to the beginning, especially because someone was late.
Okay.
Go back to the beginning, and what was the goal? What were we trying to achieve, and how is this helping us achieve it?
Okay, that second part's hard to answer. The goal for here is if you have some other thing that's not Rm, which
no,
we can.
That wasn't the goal. What was the initial goal for all of today?
Ooh.
You said it at the beginning.
Did I? I'm tripping. I guess to do calculus and differentiation on things that are not Rm.
Yes. Okay. So the goal of what we're going to do today. Last time we talked about how to take derivatives of things on Rn and Rm. Now we want to say something like this. Okay, suppose I wanted to do calculus on something that's not Rn or Rm. Okay, we want to come up with some kind of framework, right, of how we would be able to do this. What is our solution to this problem?
We're gonna transport stuff from something that's not Rm into something that's unique inside of Rm.
No, not quite. The goal is, so if that's not quite right. So we know how to do calculus from Rm to Rn. Okay, so we know how to do calculus on Rm. So what we want to do is we want to define an object which is kind of like Rm, but isn't necessarily the same. Okay. And that's what we're going to do today. We're going to define an object which is kind of like Rm, but not quite, but it will be close enough so that we can still do calculus. And now we define this charts thing. And what is the idea behind this charts thing? What is the idea behind this charts thing? You wrote it.
We can assign coordinates to objects that are similar to Rm to give it instruction Rm.
We're going to say, okay, suppose I have some object, I want to do calculus on it. I don't know how to do calculus just on the object itself. I need more structure. And the structure is going to be, what if I gave this thing some kind of coordinates, at least locally? Okay? If I have coordinates locally, then I know how to do calculus on coordinates. Because coordinates is just it's just a bunch of numbers. I know how to do calculus on that. And so we define this chart thing.
Yeah.
Okay. You had a question.
Yeah. I have two now.
Mm-hmm.
So for the second one, is it just like what's the difference on the chart and just like the bijective map from the coordinate to like the to R, like from any like does this work for infinite dimensions or like does that make sense?
Sorry, repeat the question again. again?
Like, I mean, like 247 and 240, we just talked about like the coordinate map, which is like bijective. It's like a morphism or whatever. Isomorphism.
Okay.
Why can't we just use that? Like, what is this chart thing?
Okay, so what is this chart thing? What is the chart as an object?
It's a set, but NV set.
Ooh.
It's no, it's not just a set.
Tuple?
Yes, it's a tuple of what?
An
Okay,
element
you answer.
of the set.
I'm a bit lost on the question. The question was.
Okay, the question right now is, what is a chart? What kind of object is it? It is a.
It's a tuple. It's a
what?
two-dimensional tuple. One containing a subset, and the other one is a linear. It's a linear map. It's a linear map.
Why is it a linear? It's not a linear.
Not a linear.
It's
All
just
right.
Some map.
Some map.
Some map. From U to Rm.
Mhm.
Okay. And this map has to be bijective from onto its image. And I want 5U to be open in Rm. This open condition will be relevant later for when I want to have like for when I'll add like a smooth structure to my things later. Okay. What was I saying? Yes, actually, yeah. So yeah, why does 5U have to be open? In this intuitive, like this intuitive picture of I will eventually want to take derivatives in coordinates, right? Of things. Why does 5U have to be open?
For me?
Yes. For anyone.
Oh, if it's closed, do you run into an issue with like taking derivative on the endpoints?
Yeah, that's kind of right, but not even if it's closed. I could have something that's neither open nor closed, but does something weird. The point is, if I want to take a derivative, right, I want to be able to kind of look at a point and then like approach it from kind of any direction possible. Okay? To do that, what does there have to be in the set?
Like an area around every point.
Yeah, like a little ball around every point, so that within that ball I can approach that point from every direction, and then I can take a derivative kind of, well, from any direction into any direction. So 5U, for me to be able to do derivatives on with these charts nicely, 5U has to be open, so that I just have enough directions to go in at every point. Okay, that makes sense. Okay, and 5U is bijective just because I want good coordinates, so that they're actual coordinates. Okay, so now ask them a question about like what's going to happen in the rest of the song.
Right. Did you have a second question, or was that it?
Yeah. For the first part, I think we talked about this last week. I just forgot.
Diffeomorphism.
How can you have the F inverse if like the domain doesn't have the same dimension?
Yes, it has to have the same dimension.
My bad.
Oh, okay.
Yes. Because as we know,
Mhm.
a linear map can only be so invertible.
So wait, then you shouldn't have changed that part, right? You should have changed what the dimension of U and V.
Yeah, so he did. He changed.
I did MM. You could also just erase both and put a comma there.
U is in RM, V is in RM. They have the same.
But F goes from U to V, right? Not from RM to RM. So
well, from U to V, and so you have a diffeomorphism of U and V are diffeomorphic sets.
Yeah. So U
like,
and V
I
have
map
the same
U onto
dimension,
V.
or no?
Yes, because they're both in RM.
It's like if I took like e to the x.
Yeah.
Wait, I'm.
All good. This happened to me like 2 hours ago. It's fine.
Okay.
Right.
So, right, ask them a question.
Right. Up to now, we have talked about one subset U of M, and we've been able to map it, to chart it to a specific open set in RM. That's cool, but like, we only have one like small subset. What could we like really do next? What's like a next like logical step? What?
Cover it with chart.
Excellent. So let's take it one step at a time. Let's cover a little more with charts.
Wait, hold on, stop. Did people understand the point?
Like, okay.
You can't move on until you see people are.
My bad.
Slide to the left.
So, right. What did we say we want? We said we want to come up with an object that's kind of like RM but not quite RM, and we can do calculus. We said we're going to use this idea of charts.
Yeah.
So, first question. out of all the things written here, what will end up being kind of this final object that we have, like this object we're going to construct? What will it really be? Out of all the letters here, pick a letter. What will be the fundamental object with like all the cool stuff? M. Yes. I want to turn M into like give a definition for some kind of M to do calculus on it. Okay. We have a chart. A chart is from, like you said, a little part of M. So in the end, at some point, what am I going to have to do if I want to give all of be able to do calculus on all of M?
U needs to be equal to M.
Okay,
Yeah,
that's
okay.
a good suggestion, but
You could also just place another chart or consider another little subset, like say.
so what is the problem with just having U be all of M?
You don't know if you like 5% of your own.
No. Like we're making a definition. We're just
Mhm.
trying to come up with something.
Yeah.
So if I gave a definition where just U is equal to all of M, what's the problem? Why is that not fun? Well, look at it. So if U is all of M, then phi of M is what?
It's the coordinate.
It's the coordinate now, but sorry, phi of the whole set M. That's another set. And so that is what? That is N. Phi of M is a set.
Yeah.
Okay, what kind of set is it? There's two conditions. Yes.
Some kind of object in RM.
Yes, it is an open set in RM.
Yeah.
So you're just saying, oh, M is an open set in RM, but that's not interesting. I know how open sets in RM work.
Yeah.
I don't want to, come up with some language just to have like fancy words for an open set in RM.
Yeah.
So you don't want to have something where U is all of M, because we already know this, right? So instead, what are we going to do?
Like partition.
Okay.
Like he said, we're going to try and like cover U with a bunch of with a bunch of sets, which all have this property. But then, what will I need to make sure? I'll have a bunch of these charts, but then I'll need no overlap is fine, but I'll just need to make sure that these things are what with each other. I don't want the technical word, I want the conceptual word.
I'll start drawing it on the other side for efficiency.
Not necessarily. I want conceptual word. I don't want technical.
They cover all of them.
Okay, yes, that makes sense. But the maps themselves, like what do I need to think about? The point is, I need some compatibility conditions. Okay.
And
I
that.
have a bunch of things,
Mhm.
and then I'll have to think like, okay, is there anything I need to worry about to make sure they play nicely with each other?
Ooh, that was a bad idea. Right. Perfect segue. The next part about a chart.
Exactly.
Yes.
So let me just move these things a little more this way. So
Yes. Good, they can see. So again, we start off with some set M, and we define some U phi and another VC to be charts of M. M-dimensional, always just assume M-dimensional. We say U phi and VC are compatible if this sort of like intersection between them and where they end up is open. Same for the other one. And the more jarring condition is if we compose, what do I write here? This one first? Yeah, this one first. So this takes me from if this composition is idiomorphism or diffeomorphism. Right here. Okay. I'll draw a picture. This will be explained by the picture that I will draw. Again, we start off with some set M, and we map, since there are two charts on our set now, we can map it to two separate places, both of which are in Rm. We originally had U, and now we have another, I guess, squiggly. This is V.
You don't tell apart your U from your V at all.
Oh.
And the colors are good enough.
Oh, my bad.
Just don't have the squiggle. Yeah.
Sure. Well, it's gonna make it hard with intersection, but it's fine. We have two sets.
Intersection is the other way around. Intersection is upside down. U is right side up.
It looks ugly. I don't know. So this will be mapped to someplace in phi, and this will be mapped to someplace in psi. Perhaps it's better to place it up so that people can see it. Yes. I don't know. You're here, and you're here. This is again, just to refresh, this, but applied, but now we have like two of them. We have two charts. And this statement is saying we can go sort of from here to here to here, and we can also go back. We can go from here to here to here. As to why there's an inverse and all of this and why it's a diffeomorphism, we should perhaps look at a more general case where it's not directly this to this. Perhaps is better.
Not quite. It's not anything about a more general. The question is, once again, what are we trying to do? We're trying to do calculus. Okay, very good. So just based on this coordinate idea, how am I? So first of all, what if I am doing calculus? What am I differentiating? Function. Okay. So right somewhere in the corner, any like.
There's this corner available, and then I'll flip the board so we have more space.
Draw a separate like outline. Yeah, good. Suppose I have a function from M to R. Maybe even let's write let's write Rn Rm immediately or Rn whatever Rn any vector valued function whatever, it's all the same because remember if I have a function to Rn, that's just n functions to R, so it's all the same. So following question. Right now M is just some set. I have no notion of how to take a derivative of this function. But now, suppose I had, one coordinate chart for a little piece of it. Okay? What do I then know how to take a derivative of? So I have a function from M to Rn, and this is already okay. And this is I don't know how to take a derivative of this yet. But now suppose I did have a coordinate chart for like a piece of M.
Yeah.
What object can you come up with where I would know how to take a derivative of?
Is it F like restricted to that little piece?
to that little piece, but with what? What function will I be able to take a derivative of?
Oh.
That's right.
Mm-hmm.
So write down f of phi. Okay. So this I know how to take a derivative of. What is this? This is, instead of starting on the manifold, I start at the coordinates, go to the manifold, and then do that. Okay? And this is a function from just Rm to Rn. This we know how to take a derivative of. There's no problem at all. Do you agree with this? So this is the idea. We're like giving something coordinates so that we could take derivatives in coordinates, and then that makes sense. So now, okay, we want to investigate if the function f is smooth, right? We want to take some derivatives, see if they exist, see what they are. We want to investigate if the function is if the function is smooth. Okay, so suppose it is smooth. Okay, so suppose it is smooth. Then I say, okay, well, on this thing, I know I'm going to need many charts. I'm going to have many charts, and they might overlap. And I want the key idea to not change. Right? Like I want what? I want that if I use one set of coordinates to write down my function and it's smooth,
Or this one.
then I want to make sure that if it's smooth in one set of coordinates, it has to be smooth in the other set of coordinates. That makes sense as a demand, requirement that I make. In some sense, you can think of this as, regardless of what choice of basis I make, right, what choice of coordinates I make, the kind of qualitative picture should stay the same. If the function is smooth in one coordinate, the function should be smooth in another set of coordinates for any function f, right? Like if I have any function f which is smooth in one set of coordinates, it has to be it should be smooth in the other set of coordinates. So what I want to do, I want to come up with a condition, right? I want to come up with a condition of compatibility between two different charts, such that f composed with phi inverse being smooth implies that f composed with psi inverse is smooth. Does it make sense why this is a reasonable requirement to make? Okay. And the point is that this requirement, that if in one coordinate chart I'm smooth, then I must be smooth in a different coordinate chart, is precisely the same as that. As that requirement. Okay.
Elaborate more on this.
Well, okay, you should now ask the question. What's the question you should ask now?
Did not write that down.
It's not, look, it's not about writing things down. It's about looking at the board and telling me the answer.
Ah.
So we said this.
We should assume this is smooth. So assume from the yellow to
no, sorry. I'm not asking you to explain anything. I'm asking you, I just told you a fact.
Yes.
What should you ask me about this fact?
Is it true?
No. What are we trying to do? We're trying to achieve this kind of behavior.
Yes.
Okay? We gave previously that definition. So you want to ask me what?
Can we somehow make this look like this?
Yes. Does this definition achieve this behavior? Okay? And is this necessarily are these two equivalent? Yes. So because maybe this achieves this behavior, but maybe this is too restrictive. Okay, this is too many conditions. In fact, this is essentially the same. So, okay. And now we'll elaborate on this.
Right. We will attempt to show why some specific case of this achieves this. Rough sort of way. Am I?
No, it's not rough. It's very precise.
Okay. Yeah, very precise.
Very precise.
That's questionable. I will pull this to the side because I don't believe. No, we're good with just doing symbology here. We don't need the picture. What the heck happened to the board? Okay. Once again, we have f we're gonna compose it with phi inverse, and we want, or well,
And so this is, we
You
assume
assumed-
that this one is smooth.
mhm.
Okay. Or, you know, at least one's different.
We want f composed with psi inverse also smooth.
We don't want to show that. We want to come up with a condition such that this is true. This is just what we want.
Mhm.
We don't have anything to show yet. Yes.
Can they see? Very roughly. Sorry, guys.
And we want this to be true for what?
That's jumping the gun.
No. F composed of, what is F?
F. Some function from M to Rn.
Yes. So I want to go back.
Mhm.
So I want this to be true. Like if any F composed with phi inverse is smooth,
Mhm.
then that any F with psi inverse is also smooth. Like this F is like arbitrary.
Should not depend on F.
Yes. This
Mhm.
argument should not depend on the choice of F.
So we're going to use a party trick. Well, it's psi inverse is equal to identity, right? Oh, we changed up the order here. Okay, I'm gonna have to impromptu this. So no, phi inverse composed with phi.
No. You're that's already, you've picked a choice of F. You're going too fast. So erase the identity. Write F.
Mhm.
Okay, now insert something that does not.
No, wait, my bad.
Remove the psi inverse.
Mm-hmm.
In here, add something that does not.
Psi inverse.
Okay. What should identity be?
The one at the top.
Phi.
Mm.
Yes.
Yes.
So okay, what should?
F composed with phi inverse.
Where is no? Is it
Sure.
phi inverse or phi inverse?
What should this be?
Phi inverse phi.
Okay, good.
Okay.
Why? Because psi inverse maps into M. I want to go from M and then back. Okay. Good. So now we want phi composed with psi inverse to be smooth.
Mhm.
We know that what is smooth? The no. We haven't come up with the condition yet.
Mhm.
I'm saying, you know, I want behavior. I want to come up with some condition such that if phi composed with phi, F composed with phi inverse is smooth, then the other one is smooth. So we know that that is smooth, and now you say, okay, well, what do I need to do to make what condition should I impose on something? The right part is smooth. Okay. So this is a
Want smooth?
This is yes. So this should be smooth. And so we've now now we have context for why we make that definition. Okay. Right? So the question is, this is clearly sufficient to achieve this behavior. Is this necessary to achieve this behavior? Kevin. And now you do the thing you're trying to do.
Okay.
Is this necessary to achieve this behavior?
No, it's sufficient. I know what I'm saying. Right. We're gonna try to see how this works by picking a specific F.
So, question.
Hi.
Is this sufficient? Is it necessary?
Yes.
Yes. And what you're going to do right now is going to show that it is.
No.
No, it's clear.
What?
It's obviously sufficient.
Mm-hmm.
Why is it obvious that it's sufficient?
The smooth. If this is smooth, smooth composed with smooth is smooth.
Yes. what theorem did we prove last time that shows this? Chain rule.
Oh yeah.
We all know chain rule. Smooth means like if I have a derivative for this one and I have a derivative for this one, composition also has a derivative. That's what chain rule is. Very good. So now we want to prove sufficient. So we want to show that, you know, if this works for any function such that phi composed with f composed with phi inverse is smooth, then yeah, okay. I want to show that, you know, if I want this to work, then I have to have this. Okay. And now how do you do this?
We evaluate we try a specific example. Try.
Yes.
Try f is equal to psi. Phi?
No,
I can't pronounce.
Phi is correct.
There we go. Try this, which means that we just plug in.
No. You have mixed up your letters once again. Look at the line above.
Yes.
Okay, so you want f to be phi as you wrote it.
No, wait, what? This instruction is wrong. I was going to write it from there.
Look, what you have is correct.
Mm-hmm.
There's nothing wrong. Just keep working with this thing. Okay.
No, not that.
Okay, good. So here you chose f to be phi. Why is this a good choice of f? Yeah, no, but remember, what assumption do we have to satisfy? That f composed with phi inverse is, okay, what is f composed with this f composed with phi inverse? It's the identity. Is that smooth? Yes. Of course. Okay. So we see that, you know, because we have, it's necessary, but it's sufficient by chain rule, but it's necessary because, you know, I can pick this particular f, and I get that it has to be smooth. Okay. Do you see now why this is necessary?
Loki still confused.
Okay. What's confusing?
Necessary and required, or necessary and sufficient part.
Okay. Do you not understand what that means?
Yes, but also I thought we tried f. We found out that this specific case works, and then we could show that it works for all cases.
I mean, it doesn't matter which order you look for. Like what I want to show is I want to have this behavior that if f composed with phi inverse is smooth, then f composed with psi inverse is also smooth.
Yes.
And I want to come up with a condition that achieves this.
Yes.
And I want to check, is this condition necessary to achieve this?
Okay.
Sorry. I want to check, is this condition sufficient to achieve this? What? Don't erase, please stop erasing. You're stop erasing. You're listening. Okay, I want to check. I want to achieve this. I want to come up with something that achieves this behavior.
Yes.
I can come up with a condition that achieves this behavior, but maybe the condition is too strong. Like I require too many things.
Yeah.
So then I have to check, is the condition that I came up with, is it like the bare minimum?
Yes.
Okay. And so by chain rule, I know that it's sufficient and it achieves this behavior, right? Like the phi composed with psi inverse, that being smooth, achieves this behavior. But I want to make sure that this is the bare minimum. So I need to see, okay, does that behavior imply this condition? And we just check that it does. Because what was the important part about checking that this is necessary? What was the important part of the assumption that we used?
F composed with phi inverse is smooth.
No. That is what we used to get the like. That's what we used to do the first part. In the second part, what was the thing that we assumed? What did you do? Like you wrote it down. What did you do?
Well, we plugged in f is equal to phi.
And so what does that use? That f is arbitrary. Yes. Use the fact that f that you want this condition to hold for any f such that f composed with phi inverse is smooth.
Maybe my brain's tripping. Isn't picking F mean it's not arbitrary?
No, but then you've shown like the last part has to work, right?
Yes. So you want that condition to work for any F.
Yeah.
And you want to show the necessary part. So if that condition holds for any F, then surely it holds for that F.
Yes.
So by picking that F, you're using the fact that F can be anything, meaning that F can be.
Yes.
Okay? And with this choice of F, you get that it's necessary. If that is true for any F, then it's necessary then that phi composed with psi inverse is smooth.
Yes. Perhaps I don't see the big picture.
Okay, do you see that how we showed that? Do you see what we're trying to show?
Yes.
Okay. Do you see how we showed that, this one that demanding that phi composed with psi inverse is smooth gives you the required behavior?
Yes.
Okay. Do you see how the required behavior demands that phi composed with psi inverse is smooth?
No.
That is what you showed by picking an F. You say, if I have this behavior, if that behavior is true, that implies that phi composed with psi inverse is smooth. That's what you show in this last line.
Yeah, no, this seems like a homework problem. Skip?
No, we're wasting time, but it's good time to waste. Because, we're almost done.
I just don't get how this one specific case shows that it's like necessary. Like if this,
okay. What did you do? You said, okay, so now you're going, so in the previous one, we proved this direction. We proved that if that is smooth, then that holds.
Yes.
Now I want to prove the opposite direction. Suppose F composed with phi inverse is smooth and F composed with psi inverse is smooth. For any F such that F composed with phi inverse is smooth.
Yes.
Okay, suppose that is true. Then, if that is true, I can pick F, and I know that phi composed with phi inverse is smooth.
Yes.
Then, by assumption, phi composed with psi inverse has to also be smooth.
Yes.
Do you agree? Phi composed with psi inverse is then equal to phi composed with psi inverse.
Yes.
Okay. And therefore, phi composed with psi inverse has to be smooth.
Yes.
Okay, so you've shown the opposite direction. If you have the left hand side, the right hand side holds. If you have the right hand side, the left hand side holds.
Yeah.
Okay, and the bottom line is showing that left hand side implies right hand side of like the top two lines. Okay, you know what? Sure, let's continue. I think the point is clear.
Right. No more space here. This is more useful now. And I will move on to the next page. Okay. We have sort of up to now defined behaviors on if we have set M and we have multiple charts covering it. And as our classmates idea said, well, what if we covered all of M with just a whole bunch of charts? Can I pull this over? I can. Wonderful. This leads us to the next part. Right. Okay. Definition. Again, we say an atlas is a collection right on the other side.
So now we're just gonna do. So now we're just gonna do this thing that we said, like let's just cover all of M, and we know that this is a compatibility condition I need to be able to have a good structure for doing calculus, and okay, so now I just take a bunch of them.
So conditionally, ooh, I wrote you like this, right? Right. That's the part I was worried about. So you can cover M by all the little domains you picked for your charts. And second of all, I'll have the wrong thing. Okay, if you have any two U alpha, phi alpha, phi beta, compatible. If you are in this collection of charts, then any two charts in the collection should be compatible.
According to the definition we had on the previous one.
This is an atlas.
So an atlas is just a bunch of
It's just a bunch of charts stitched together.
that cover the whole all of M.
You can I might not write this down. You can keep adding charts to cover your, or well, that's a bit redundant.
Wait, are two of the same chart?
Is the same, yeah, so you have to check if a chart is compatible to itself. Okay, but is it compatible to itself? Of course, because phi inverse is the identity, and that's smooth. And you know, bijective and open, all the open set conditions qualify. Good. Okay.
Okay. I might have made a small mistake in my notes. You're gonna have to correct me. You can keep adding charts to your atlas up to the point where it's like completed. So if A's are atlas is equal to some collection of U alpha.
Yeah. You have charts and then you put them in an atlas.
Very intuitive.
Yeah, makes sense.
This we consider maximal when this is just equal. Yeah, rhetorically, when you add all possible charts to your atlas, you get a maximal atlas.
Like necessarily can also fill out.
So
This is part of
the
it, right?
claim is that okay, suppose I have some atlas, right? Then in principle, I can like maybe add another chart to it that's going to be compatible to all the new charts, to all the old charts, right? And the point is, a maximal atlas is I take some atlas and just add everything that I could possibly add that's compatible. And such a thing exists. So one thing you have to be careful about and technically prove is you want to show that, like, suppose there's one chart that's compatible with all of the charts in an atlas, and then there's another chart that's compatible with all the charts in an atlas. Are those two compatible?
Is it like what's that thing called? Symmetry reflection?
Yeah, like that kind of thing. You can think of this as kind of like an equivalence relation. And so the question is, you know, are they? Of course they are, because compatibility is like, can I go from one? Can I do like a change of coordinates? And is the change of coordinates smooth? Okay. If the change of coordinates from this one to any of these are smooth, and from this one to any of these are smooth, then I can like change coordinates into this one, and then change coordinates into that one.
Right.
Yeah.
Though I will add, I think Book mentioned that compatibility is not an equivalence relation.
Compatibility is not an equivalence relation?
Wouldn't that mean that you can't?
Maybe it's
Book says it's not. I tried to verify it. Like it sort of makes sense. I can't see why it wouldn't.
Maybe it's not. There's probably some simple condition that's missing.
Compatibility, you mean compatibility and well-defined of smoothness are not prevalent according to the book? They are.
No. I think he's saying that
If
compatible is not an equivalence relation on the side.
So if chart A compatible with chart B compatible with chart C, chart A not necessarily compatible with chart C, which is strange. That's
No. It has to be. It has to be.
Yeah, that's okay.
I think it is. Sorry.
Then like
A with
you
B.
could just how would the
Exactly. I don't know. Maybe I'll just like read the book again. But I remember some quotes saying you can't exactly think of it as equivalence relations.
Yeah, like that one should
It
be-
shouldn't break any of them,
Okay. Anyways, keep going.
right? I will now present on manifolds. I can erase this.
And now we want to, come up with our final definition of our object we want to study.
This was yours. These are all yours. Okay, can't be mistaking them.
It is on. So let's see. A parallel B. You might not. What you might not have. Something about the intersection of open sets.
I think maybe you see when you compatible between A and B and B and C, you're completely missing the intersection of A and C, which is not in B. So maybe things
Oh
are
yes,
there.
yes, you're right. Yes, that's true. That's the like the
Intersection?
The point is if I had like 3 sets, and I kind of compare A to B and compare B to C, right? A intersection with B could be missing out some things that will be in the intersection of A with C. Okay, so you're right. It's not exactly an equivalence relation because of that. Because I can draw like 3 sets overlapping, such that A with B has A with C has something that A and B doesn't together.
Say something like this.
That's the compatibility. Yeah, exactly.
Or this, or this.
See, like yellow and pink, purple. Yellow and purple have an overlap, which yellow and green don't. So it's not quite.
I'll just do this.
But the point is that if you were to, okay, yes, this is a good point. But you still, a maximal atlas still makes sense. Why? Because I'm not asking if, my new chart is compatible with like one single chart. I'm saying is it compatible with all of them? But all of them together cover the whole thing. And so then I could kind of look at every chart and then I can, stitch the compatibility for this one together.
You're like checking each of them independently.
Yeah,
Yeah.
like break it up into whatever.
If we look at the 3 colors, like if that's our whole space, like those 3 charts would
Yes.
make up an atlas.
Would make up an
But
atlas
it's not
if
in maximal.
Yeah, if it was
It
small.
doesn't have the atlas for all of the like intersections between only 2.
yes, yes, exactly. So I need to I can keep refining it more and more
Until
by
they all
looking
like
at,
intersect.
what I could do is I could look at the coordinates.
Should I draw it one more?
No, hold on. I can look at the coordinates, and in the coordinates, I can then look at like an open ball inside of the rectangle, at every possible open ball inside of the rectangle, and that gives me like a bunch more charts for open sets, kind of over there.
So would the maximal atlas be like the topology generated by like this if you view it as a subbasis?
I think that should be close.
Okay.
I think that's essentially right. That's right. I like. There's nothing obviously wrong with it,
Yeah.
and that's how I often think of it. But maybe, and yes. So the point is that after this, what you'll be able to do is before M was a set, then using these coordinate charts, you'll be able to give M a topology if you want to.
Right.
Okay. And, keep
My
going.
part.
Let's get
Would the topology be reasonable in some sense? Just a way to just give it discrete topology and everything would be continuous, but
I don't want everything to be continuous. Then I can't tell anything apart.
yeah. So would topology be actually construct anything?
I'll write it down.
It will be good enough for the purposes of me comparing this object to Rn. Right? If I give it, like, the point is, we want to come up with a new object that's kind of like Rn. And we're going to give it a topology that locally is like the topology of Rn. Globally, maybe not. But locally, the topology will be like Rn.
I mean, you don't want it to be too fine in some sense. Like
It will be exactly fine, like, I agree. But once again, the goal is that locally the topology is that of Rn. And it will. because that's literally how we, we give it that in some open set it is the same as a set in Rn. So we literally give it locally we give it the topology of Rn. Globally it might have something more complicated, but locally it literally looks like Rn.
Maybe another question. I mean, what I understand is that from the charts, we are constructing back a topology on M. Is that what you're doing?
Yes, that is what you can do.
Yeah.
That's right.
So we don't have any, let's say, properties of coarseness in some sense, because when we don't want it to be too fine, as you said, what sort of properties are we expecting from it to have?
Well, we are expecting like if a function is continuous in the charts, the function is continuous on the manifold. And vice versa. If the function is continuous on the manifold, it's continuous on the charts. That's what we want, and that's what you will get from this kind of that's exactly right. You want we will by defining a topology in the charts, that's actually saying like if it's continuous in the charts, it's continuous in the manifold. And if it's continuous in the manifold, it's continuous. That's great. That's what we're trying to do. Okay.
Me? Right.
I mean, you can.
Okay. As I was saying, we can define now the big structure, I guess, if you can call it. Oh, I hate this U, man. So a manifold is just a set M, but you equip it with a maximal atlas. You can cover all of M in some way. You can describe it in Rm, and you can transition between them with two extra conditions. Firstly, the number of charts that you cover it with, it must be countable, or you see finite, not basically never finite, but countably infinite. You can assign some functions from naturals to each individual chart. And number two, yes, but you can count them. You can count them. And two, I won't put the name. I'll just put the direct definition.
And that we need because there's some like particular behaviors that we want to, like edge cases that we want to avoid from happening.
Or I like this to save space. Sorry. There. The intuitive explanation for this is if you have 2 points that are both.
What is this? Sorry, you just wrote something down and you should either read it out loud or like something so that people have time to process.
Right. If you take 2 points inside of your manifold M, and the condition that we impose is these 2 points can't really act identically. In rough words. Can I draw the picture? Say you have something on the reals. You have this line, and we have 2 such like origins.
First, you should draw a picture for the condition. What does the condition mean?
Condition?
You wrote down some condition, right?
This.
No, that one is whatever. The second condition.
That.
Draw what it means for the manifold, and then do the example.
So not this?
No, that's just an example of what we want to avoid. I want to give like a generic, generic picture.
Generic picture.
So like draw a blob.
Right.
You don't even need the charts.
Make them bigger, better.
Yes. So you want to say, let's take any 2 points. Look, stop
Mhm.
drawing. Erase. Okay. When you draw a picture to explain a statement.
Yep.
So read the statement. It says.
For distinct points P and Q and M.
Okay, so you should draw points P and Q and M. Okay, good. There exists what?
There exists two charts.
Okay.
U alpha, phi alpha, and U beta, phi beta.
Okay, such that.
Such that P belongs to
Okay, P
one.
belongs to one. Q belongs to one, but overall they don't
intersect.
Okay, good. So draw how this looks like. Okay, good. So we now additionally impose this condition on the which atlas? On the
Manifold.
maximal atlas.
Oh.
Right? So I want to make sure that if a manifold will be something where the maximal atlas has this property. Okay, good. And why do we impose this property? This property lets me do what? It lets me tell apart what? It lets me tell apart any 2 points using what? Using a chart, not quite the word that I want, but like these charts, I'm going to use these charts to tell you which functions are differentiable / continuous. Because this whole definition is essentially setting me up to do what? I'm going to think of charts, think of functions on my manifold as functions in the coordinates, and I'm going to say, okay, it's smooth if it's smooth in coordinates. And so what I want to do is I want to be able to distinguish between points using functions. Do you agree? So in some sense, do you remember what we mentioned yesterday? So
very briefly.
Oh,
I can't even draw.
There should exist a smooth function that is what? This condition is equivalent to there being a smooth function that is what at these 2 points? Okay, what if I have a function and it's evaluated at 2 points? What can it be? It can be, or
Well, it should be different.
Yes.
If there are 2
good.
points, like no 2 points should get the. You shouldn't get the same answer for 2
so
points.
The point is, for any 2 points on my manifold, so this condition, and we're not going to prove why, but this condition is equivalent to saying the following. For any 2 distinct points on the manifold, there should be some function which is either continuous or smooth, depending on what kind of manifold you have, which has different values at these 2 points. Okay? Now explain what kind of examples this avoids. Give an example of like what does this condition avoid?
If you have a real line and you have like an origin, say you have 2 distinct. Yes.
Sorry. Doesn't the first condition substance avoid substance guarantee the third? Maybe.
No. We're about to see an example when it doesn't. Give an example.
There are 2 such like points. One might be.
Okay. Sorry. What is this?
This?
What did you draw? What you drew is in front of you, not above.
Well, no, it's just, I don't know. This is not a manifold.
Yeah, this is not a manifold.
Yeah, wait, what?
We're giving an example of something that's not a manifold,
Mm-hmm.
and we don't want it to be a manifold. Okay, what is this? What did you draw? What is this example? This is the real line, and what do you do to the real line? Okay. What do you have drawn on the board in front of you?
According to what we discussed yesterday, 2 origins, 2 points.
So you're
that
saying
seems.
that you have the real line,
Yeah.
and you add another point.
Sure.
Okay. This is what he has drawn. You have the real line, and you add another point. It's just that he drew the origins kind of separated, so you can see that there's 2 of them. And now you can give 2 charts. What are the 2 charts?
Something possibly like goes up here.
And
another one that maybe goes from below and it excludes this point.
sorry, what you're okay.
Exclude,
This
no?
is not clear what you're drawing. What are you drawing? So I need to define charts, right? Which map from my set M into the reals. Okay. And here, suppose my set M is this real line with an extra point that's kind of at the origin. So I can define two charts. One kind of maps this thing into R, and it sends, you know, the top origin to 0 and just forgets about the bottom point. Okay, and then I can have another one which sends the bottom point to 0 and forgets about the top.
Let's put it a bit farther away.
No, they should be at the same place.
It should?
Yeah, they're both
No.
the origin. They're at the same place. Do you see? And so I could give two charts. Okay.
Do I still do the thing? No, bar intervals, right?
Let me just write. So I can define. I need a chart. I can define one chart phi, which kind of sends this point to its associated point on the real line, okay, and then sends kind of this point to 0, okay, and then I can define another chart psi, okay, that sends everything here like this, but then it sends this point to 0 and kind of doesn't consider this point. Okay? So the chart phi is from what set to what set? The chart phi is from, so this is R union, I don't know, union the yellow point, and suppose the green point was already there. So this phi is from where? Phi is from R union yellow minus green, right? Do you agree? Into R. That's the yellow chart.
Yes.
Do you agree? And then psi is from this R without the yellow. It's just R union green. So just from R. From R to R. Okay? Do you agree? And okay, first of all, this is yes, and so these are compatible charts with each other, right? Because you know their intersection is this and this set. Their intersection is this and this, kind of excluding the origin. And there, the transition map is just the identity, so it's smooth. Do you agree? But I cannot tell apart these 2 points from each other using these charts at all. Do you agree? And so that is a problem. The other thing is like, you know, yeah, the other thing, like, I don't want this kind of thing to be a manifold. Like, this is strange. And like, yeah, I don't want this to be in my definition. And so for this reason, I say there has to be in the maximal atlas, there has to be at least, you know, some open set that I can draw that will separate this point from this point. Because look here, you know, if I draw any open set around it, the degrees will always, if I draw like a ball around this point versus a ball around this point, they will always intersect. Okay, so I want to not have this. So I want to say that there should always exist at least some kind of open set around one point and an open set or another round point, so I can tell them apart. Okay. Do people see why we want this condition now, based on this example? Does that answer your question from earlier? Good. And this is called the like Hausdorff property. In topology, you learn about like the Kolmogorov classification or whatever, the separability axioms.
Yes, that's nice.
That's one of them.
Okay.
Okay.
Done?
So what's a manifold?
Some set M,
Okay.
that you equip it with some atlas or a complete collection, a maximal complete collection of charts, such that you can count all the charts. You can count them even if they're infinitely long. And if you have two distinct points, they should be in separate charts. You can't have both points included in the same chart, or else you would run into this problem where you have a function approaching the same value for 2 points, which is strange. Now that we've defined this, we want to see an example. So
Use the central board.
central board, this one?
No, the one behind.
I see. Then this will be erased since it's our first.
Actually, no. Maybe use the old
Yeah.
board so you have the definition and use this one. Like, sorry, keep that board and then erase that.
Keep this? No,
Keep the definition and give an example so you can compare it to the definition.
no, yeah, but I gotta erase one. This one goes, right?
Where's the definition of the manifold written? Which board?
Here.
Yes, you want to keep that. Probably. Actually, wait, sorry. This is.
No, so I thought we used.
Okay, whichever one. Doesn't matter. Either one's fine. Actually, maybe you want to use this. Yeah, keep this.
What are we using?
I mean, actually, yeah.
That, no? This gets
sure,
erased.
Sure, that's right. You use all of them. Go ahead.
This is mostly useless.
So now we
Everything
define
here.
this object
Mhm.
where it makes sense how to do calculus on it. Because I have these coordinate terms and I can do calculus with coordinates. And okay, if you had a bunch more time and a bunch more effort, then you can say, oh, I can give M a topology such that if a function is continuous, if a function is continuous in coordinates, then it will be continuous on the map on M. I can use coordinates to give M a topology. And so, yeah, you have smooth manifolds and topological manifolds. Smooth manifolds only require that psi phi inverse is a homeomorphism. We want to work with smooth manifolds, so we declare it to be a diffeomorphism, demand it to be a diffeomorphism. But essentially, like those, that compatibility condition, you can like tweak it a little bit to get a slightly different structure. It's whatever.
Great.
Okay.
Example. How's this calling? Right. Specifically, we want to see a serigraphic projection from, I guess. No, what am I saying? Consider S1. This is a set of x and r squared. We'll say this is just a circle. This is the unit circle, centered at, well, the center of our axes. This is our unit circle, and so we want to be able to map a point in our unit circle, which is one-dimensional, onto like another point inside of like R2, or no, inside of just R. Right.
The circle is one-dimensional because you stand on a circle. How many directions can you go into to stay on the circle? Yeah, so there's one direction.
It's a weird def. I said no good. We'll draw this thing in. How do I want to organize this board? Analytically inverse. Correction. Perhaps I do want to draw this here. And perhaps, no, this is useful. It's really a wax circle.
So now what do we want to do? We want to turn this into a manifold. So we want to give it some charts. Okay. So let's give it some charts.
Right. We're going to give it two charts. I'll call them north, and I'll call this one south, represented by N and S. This chart, or well, I should first describe what my subsets are. Un is just equal to S1, but we get rid of this top point. All right, it's an S3. All right, what's this? 0, 1. And fittingly, US is our circle, but I get rid of this southern point, -1. For purposes, I'll draw 2 empty circles now. We have our domains for the chart. We have to define the mapping from our like domain onto the real. Wait, did I write that down? I don't need to write that
Onto
down.
some open set in the real line.
What we're trying to do, a way to illustrate this is if this were ours, this is just reals. If this line indicates our reals, we can connect a point here to some point P in S1. We can draw this like a line that will intersect the x-axis, which is our reals, at some point. This will simply be, well, we're going from the north. This is phi n of P. This point.
So we define a map phi n using this kind of picture. And so then, okay.
We can analytically solve for phi. That's just rate over run, and then you times c because that's a rate, and then we make it equal to 0. You bet that phi n is equal to and phi s is equal to x 1 plus y.
Let me see if that's right. So,
What you got, right?
Hold on. Okay, if people believe that this is right, then go ahead.
Once we do this, we want to sort of verify that it actually is manifold. Two of the conditions we need to check are that, well, mainly this. It's mainly this is the thing that we want to check.
Yeah, we want to check that. We want to check that okay, those sets are open, but sure they are. Because if you look at the picture, what is the image of phi n?
Perhaps a different color.
What is the image of phi n? No. The image. So the phi is a function that takes a point on the circle and draws this line and looks at where it intersects. So what are things I can get? It's no, including 0, because the North Pole.
Oh, because
if I draw something going directly down to the South Pole from the North Pole, well then that the North Pole gets the South. If you're looking at phi n, where you exclude the North Pole, then the South Pole gets mapped to 0. Yeah. Yeah. So it's the whole real line. That's of course open. So that's whatever. Everything is nice. Yeah, their intersection would be just the two halves of the real line, excluding the center. Right. Actually, so quick question. In this picture, why does the North Pole not get mapped to anywhere but phi n?
Like open it up, it would like be the same spot as the South Pole.
Go again.
So in this construction, if you tried to map the North Pole somewhere, where would it be going? Like if you draw
like
this
if
line.
P, I kept pushing P all the way to here.
No.
What if P were like here?
What if you were like very close to the North?
Yeah. What if it's like P prime here?
Where are you? Where does that get mapped on the real line? If you're getting closer and closer to it.
Exactly.
Yeah, to infinity. So if you try to map the like literally the North Pole somewhere, you get like a horizontal line which doesn't intersect the R at all. Right? So
yeah,
exactly.
that's why we exclude
You're
it.
dividing by 0, so it doesn't work.
That's why we like kick it out. We kick that point out, and so we're happy. But since we kick this point out, we need the other one, which is we have the southern projection.
Which is why you need 2 charts. And this is the whole point of like why I didn't want all of U to be M. U to M to be covered with a single U, because you actually can get something non-trivial where you have something where locally it looks like an open set of R, but it's not at all the same as an open set of R, right? Like you don't have anything in R that looks like a circle. Okay, and in topology, actually, you learn this quite soon. In some sense, like draw an open interval. Just draw an open interval. Okay. So intuitively, suppose I remove a point from this open interval. This now becomes what? It's the union of two distinct open intervals, and I can't really get from one side to the other. Right? But suppose I had a circle, and I remove the point in the circle. I can still get from like any part of the circle to any part of the circle because by going around. And so you can see that, in some sense, the circle is somehow very different from an open interval. Okay? Because I can remove a point and then I get different things. Yeah. So, this is kind of giving us insight that this thing that we define, this manifold business, is actually something like it's a new kind of object. That's not something that we already understood perfectly well just with calculus as is. Okay, and so now if you want to check the compatibility condition, what do you want to check?
So you're saying like it's like these manifolds are basically like just different ways of showing things that are already.
Yes, like this is something new, conceptually new. Yes.
Can we say that, for example, an atlas always gives rise to a unique maximal atlas, so we don't need to worry about all of them?
Yes. Because a maximal atlas is like, if it's compatible, I add it. Right? And so the big thing you have to prove is that if it's compatible with this atlas, then it's compatible with anything else that you can add. So kind of the order in which you add things doesn't matter. And you can just add everything at once. Is that, yeah. So that's right, the maximal atlas is unique. Because you just say, if it's compatible, I immediately add it. Like, look at all of the set of all mutually compatible things. And then the point is like the order in which you add things doesn't matter, so you're good.
But there's only one maximal atlas for any manifold.
So if I have an atlas, then there's a unique maximal atlas. But I could have like I could give the same manifold different structures. In principle.
Like rotate this one, right?
Well, no. If I rotate it, then the maximal atlas is the same. Because that one should be compatible with this one if I rotate something. Yes.
Well, something that might happen is that in this case, for all open sets, there are a few charts. There are a few different maps. Would it be okay?
For all open sets, there's only a few different maps.
For each open set, there's more than one chart which has that open set as its open set.
Oh yeah, that's fine. As long as the coordinate transformation is smooth, you're good. Like the what you're saying is, suppose I had a city and I had a map for the city, okay? And suppose I rotated this map. Is it still a good map? Of course it's still a good map. I just rotated it. But it covers the same patch of the city. But I rotated it so the coordinates are a little different, but the vibe is still the same. Yes. So yes, you can have different charts that have the same U and they're different coordinates, but whatever. One thing I could do is I could swap x2 and x1. That still gives me some coordinates. It's different, but it's still compatible on the same U. Okay, maybe that's not clear. Okay. What's one thing we would want to check on? And this is probably where
last thing.
Almost done here. Yes. So what do you want?
Namely, if we can go back. Check if these are first of all invertible. Like we saw a 5 inverse, right? So we want to make sure these are invertible.
You want to make sure that this is bijective onto image.
If I didn't mess up, they are.
Okay. I mean, also you can like look at the picture and see, well, of course, because it's like whatever. That's not going to get you many. Like you may not earn the most marks that way though. In 327, you may earn many marks that way in 1301 though.
What's 1301?
Or 1300 as well. In the grad topology courses, you just kind of draw pictures and say like, yeah, of course it does. It's like just look, like clearly, just look at it, and then you're like, okay, 1,000 points. Because to like actually write down all of the things like rigorously would take you 1,000,000 years.
Mhm.
Like to actually write down like a proper map and actually take the derivative of that thing of some of those things is like no one has the time. Or it's like showing that something is continuous.
My favorite is getting points for saying like by computing you can see that.
Yeah.
I
And then you don't actually
repeated information by parts.
Right. Brief sanity check of why this is true. You have the same x, but the y differs by a factor of negative, which is true because our y is like on the negative side. If I got different things for x, we'd have a problem. So that's a way you can check your work. They are invertible, and now we want to compose them. And the composition is supposedly infinitely differentiable, and the inverse of the composition is infinitely differentiable.
Yeah.
Well, should I do it?
I don't know. You know what? Maybe let's leave this as an exercise. Like, yeah, like just take this, do this inverse to yourself, and check, take the derivative. Now, actually, I can tell you right now what the answer you should get should be.
Okay.
If someone guess, or at least yeah. So if you were to look at phi n and do phi n composed with phi inverse s, phi inverse
S.
Okay, what will this map be? Can you guess? No. Remember, you have to have like the point at infinity is going to get mapped to 0, and 0 is going to get mapped to a point at infinity. Okay, complex analysis and joy. What should I get? What should I get? Phi n composed with phi s inverse.
No.
What is it? What is the answer for a sphere in complex analysis? No. You have to.
No, I'm not answering.
Okay, sure.
Maybe inversion.
Yeah, that's right. I think if you compute that, you should get like 1 over t. Which you know from complex analysis, because that's the you're right. Why? Because okay, well you can compute it and you can check, but also you can see kind of the North Pole in the north coordinates, it in some sense gets mapped to infinity, but then in the south coordinates it gets sent to 0. So okay, maybe it's 1 over t. Okay, and you can check that it is.
Right. Should I
yeah.
create the example for a sphere?
Yeah, and then so just say kind of the same, draw the same picture,
Right.
with some minor modifications.
So, model 2. This is for a circle, S1 in R. We're going to try to elevate it a bit. Consider a sphere. Oh, this tiny drawing. Consider a sphere. A sphere can be characterized, it's two-dimensional, it's S2. R3, yeah. Blah, blah, blah. Radius of 1. We can characterize this sphere by 2 degrees of freedom, and then you can also map it. We're going to attempt to map it to a plane. Oh god, this is terrible. Something like this. By saying, here's the North Pole. We're going to draw a 3D line from this North Pole to somewhere on this plane. Let's say it intersects here, and then it'll go past.
Yeah.
You're going to map some point, I guess, on the circle.
On the sphere.
Sorry, on the sphere, and then you're going to hit the XY plane. Yeah. And that's how you can
so it's the exact same thing as before, but with the plane. In fact, you can do this for a sphere in any dimension. You'll always have a north chart, a south chart, and it's always going to be exactly the same. You take a point on the sphere, you connect it via a line to the North Pole, and see where that intersects the kind of plane that intersects the sphere. Yeah. And then you can compute. It's not too hard. You can compute all the inverses and whatever, and show that it's 1 over t or 1 over t. 1 over t. Yeah, 1 over t. I think. Or maybe something like that. So you should definitely maybe write this up as a suggested exercise.
Okay.
You should definitely do the circle. you should do the sphere once, because then it appears in complex analysis. Yeah, you should do this. It's a standard exercise. Okay. What's another way that you could parameterize the circle that's a lot easier? Suggestion.
Parameterize a circle.
Yes. So you want to give a different coordinates to the circle that don't use this nonsense.
Not confident in my answer.
Yeah.
Polar?
Yeah, you can just do trig.
Trig?
You can just do
Polar?
cos t. So arc cos and arc sine would do that. So yeah, polar.
No, but you need two, right? We want to use one. We want to map it to like R.
Exactly.
You
so you have one point on the circle, and then do arc
sine or arc whatever.
Arc
Yeah,
tan,
just one works.
One of them, and then you could. But then you need like 4 charts maybe. Yeah, one for each quadrant, and then that's maybe a bit more now. But also like cosine is like, I don't know what cosine is. It's really hard.
I couldn't see. I'm so sorry.
You know, at best you get rational functions, but I know how to deal with rational functions. Trig functions are like, this is too hard. I don't know what that is. Oh, like infinite power series. No. It's too complicated.
Right.
Okay. I think this is pretty good. Yes.
And this is like the main takeaways.
We defined an object on which we now know how to do calculus, and how we did this is we just give the object coordinates, and then we do calculus in coordinates. That's it. Yeah. Okay. Were there any questions online?
No, there isn't.
No, there was someone on.
One person.